Hello everybody. In this video, I'm going to show you some of the example problems from chapter 6. Okay, now let me share my screen with you and show the first problem with what we are going to solve today. So this is the first problem. You can see this is a column here, which is 3 meter, 2 meter size. And the depth of foundation is 1.5. And your phi prime is 25 degrees. C prime is 70 kilonewton per meter square. A factor of safety is 3. They are asking to find out the net allowable load for the foundation can carry. Okay. So if you see any problem like in chapter 6, the first thing you have to take a look the location of the water table. And the second thing you have to see the eccentricity. Is there any eccentricity there or not? So here, if you see there, the load is working at the middle, so no eccentricity here. But if we can see the water table is above the depth of the foundation, right? So this one is basically case 1. Now, let's go to the board and try to do the problem, okay? Okay, so here is the figure of the problem. I just draw that one in the board. Now, as I said earlier, that you have water here, so the pressure Q at the bottom of that foundation would be this one, let's say D1 gamma plus D2 gamma sat minus gamma W, which is actually 17 into 1 plus this one is actually 1 and this distance is basically 0.5. Okay, so this is 0.5 into 19 minus gamma W, which is 9.8. So your Q is basically 21.85. kilonewton per meter square. Okay. Now, actually, we have to take a look like what is our phi. So, phi for this problem is 25 degrees. Okay. So, your NC NQ and N gamma, we have to find that out from the table 6.2. Okay, let's go to the table and see what are the values for our NC, NQ, and N gamma for phi equal to 25 degrees. Okay, your phi is basically your bearing capacity factors are basically the function of your phi only. Okay, so let's go there and take a look what is the value. So this is the bearing capacity factor, NC, NQ, and N gamma. Then this one is a function of your phi prime. For our particular problem, you can see our phi is 25. So our NC is 20.72, NQ is 10.66, and 10.88. That's basically table number 6.2 in your book. Okay. Now, other than the bearing capacity factor, you also need the shape factor, depth factor, and inclination factor. for this particular problem, there is no inclination. So all the inclination factors would be 1. Okay. And you can see this is the shape factor that we are going to use for our problem, but we need to check this one for our depth factors. You can see that all the equations given here is actually this one df by b. So df in our problem is 1.5, b is 2. So actually df by b is less than 1. So we are going to use this page, not this page here. Okay. Now we have to take a look about our phi. Phi is 0 or greater than 0. For our case, phi is 25 degrees. So basically, we are going to use this equation to find out our depth factors. Okay. Now let's get back to board and try to do the problem. So your NC is 20.72. Your NQ is 10.66. And your N gamma is 10.88. Okay. Now you can see that our shape factors are FCS is basically 1 plus B by L into NQ by NC. We already told you that this is our L and this is our B. One more time, like the longest, parameter is your length and the shorter one is your width. Okay. So when they say 3 meter, 2 meter, this means like 3 meter long and 2 meter wide. Okay. So here is your NQ by NC, which is 10.66 divided by 20.72. That's basically 1.343. Similarly, we can find out our FQS, which is basically 1 plus B by L into tan phi prime. So that's actually 1 plus 2 by 3 tan 25 degree. That's actually 1.31. And your F gamma S is equal to 1 minus 0.4 B by L. So this one is 1 minus 0.4 into 2/3 of that, which is basically 0.73. Okay. Now you already saw that one, then there is no inclination here, so inclination factors are all 1, right? So I can just write it down here that FCI Now depth factors. So FQD one plus 2 tan phi prime 1 minus sine phi prime square df by d. df is the depth of foundation, which is 1.5, and d is actually 2. So this one is basically 1 plus 2 tan 25 into 1 minus sine 25 square 1.5 divided by 2. That's basically 1.233. Similarly, our FCD is equal to FQD minus 1 minus FQD divided by NC tan prime phi, tan phi prime, sorry. So this one is basically 1.233 minus 1 minus 1.233 divided by NC, which is 20.72 tan 25. That's basically 1.257. Okay. Now, our bearing capacity I'll just keep that one here. So our bearing capacity QU, that's basically C prime NC FCS FCD plus Q NQ FQS FQD plus half gamma prime, because the foundation here is actually under the groundwater table. So we have to remember that one here, that we have to use the gamma prime here. And then B and gamma F gamma S F gamma D. Okay. So if I plug this value here, so you can see this one would be 70 into 20.72 into FCS, which is 1.343 into FCD, which is actually 1.257, 1.257 plus Q, we already calculated that one, NQ, which is 10.66 into FQS, 1.31, and then FQD, which is 1.233. Plus this part here. So I have, this one is actually 19 minus 9.8. Then B is 2. Then gamma is 10.88. Then gamma is, this is 0.73. And actually by default, your FC gamma is equal to 1. Okay, 1. So now I can take this part off because I already put all these values here. And you see your QU net is basically your QU minus your Q, which is basically that Q is, you already know, which is actually 21 point. Okay. And then your total Q, that would be QU minus Q multiplied by the area of that foundation, right? Area of the foundation, which is actually 3 into 2. Okay, that's actually ultimate net. And then Q allowable net, that would be QU minus Q into area 6 divided by the factor of safety, which is basically 3. So this one is basically 2 into QU minus Q. So if you try to find that out, that would be the whole thing here minus Q 21.85, okay, and then multiplied by 2, that would be actually 5760. That many kilonewton. Okay. The two things you have to remember here, that when you are putting that equation here, then basically Q is the effective stress at the bottom of the foundation. Okay, is always effective stress. So you have to take out the weight of the water if it is submerged. And then like this gamma is always the unit weight just below the foundation. Okay, so since the water is submerged, since the foundation is submerged, then basically your gamma will be always the submerged unit weight. Okay, now let's move forward. So this is the second problem I'm going to solve here. You can see if I read this problem, and an eccentrically loaded foundation is shown below. Use factor of safety of 4 and determine the maximum allowable load that the foundation can carry. Use Meyerhoff's effective area method. Okay, so this is just one-way eccentric. You can see the foundation is 1.5 into 1.5. This means this is a square foundation, and this is the load applying here, which is actually 0.1 meter away from the center of the foundation. Okay, so this is just one-way eccentric. Now you can see here, since our phi prime is 32, so from this table we can find out the bearing capacity factors before we go to the board. Okay, so for 32 degrees, we can see our NC is 35.49, NQ is 23.18, and N gamma is 30.22. So I'm going to use this value to do this problem in the board. Okay, let's go there. So this is the drawing for problem number 2, like the second problem here. You can see here that the force is working like 0.1 meter from the center of the column. So your EB is basically 0.1 meter. Okay, so the effective width B prime is basically B minus 2E. So which is, you know that B is 1.5 into 1.5. So this is a square column. Okay, so B is 1.5 minus 0.1 into 2, sorry, 0.1 into 2, that's basically 1.3 meter. Okay, now this is a one-way eccentric. Okay, so we are going to use the Meyerhoff's effective area method. Okay, so you can also see here, since our phi is 32, your NC, NQ, and N gamma, the bearing capacity factors, you can just get that one from the table, as I showed that one in the previous problem. So for 32 degrees, actually your NQ and N gamma (23.18) and N gamma is 30.22. You can see that I didn't find out NC here because the cohesion for this is 0. Okay, so the first part of the bearing capacity equation should be 0, right? So the equation we also know that there is no inclination here. So basically all inclination factors are also 1, right? So the equation for QU, it's basically Q, NQ, F, QS, and FQD plus half gamma D N gamma F gamma S F gamma D. Okay, and if, as I said earlier, that you have to take a look like whether there is water here, but we don't see any water table here, so you don't have to worry about that. So this is purely eccentric loading problem. But many cases you can have water table near the foundation. Okay, in that situation, you also have to take care of that part too. Okay, so here we are just going to find out these 4 factors here. Okay, so you can remember that to find out the shape factors, actually you have to use the B prime value, right? The effective width value. On the other hand, to find out the depth factor, actually you have to use the original value of B. Okay, now let me show you how to do that one. Okay, so here is your shape factor. So FQS, that's basically 1 plus B prime by L prime. Tan phi prime. So you can see here, actually I'm using 1 plus 1.3 divided by 1.5 because my L prime didn't change because there is no eccentricity in the L direction. So this is basically 0, so that's actually 1.5 minus 0 equal to 1.5. Okay? Tan 32 degrees, that's basically 1.54. Then F gamma S, this is basically 1 minus 0.4 B prime by L prime, which is actually 1 minus 0.4 into 1.3 by 1.5. That's actually 0.653. Now, depth factors. So FQD, that's basically 1 plus 2 tan phi prime 1 minus sine phi prime square, and then df by b. Okay, so this one is 1 plus 2 tan 32 into 1 minus sine 32 square, and df by b, which is actually 0.8 divided by 1.5, which is basically 1.147. So you can see here, actually, I'm using B, which is the original width, to find out my depth factors. Okay, that's very important thing that you have to remember. Okay, similarly, the other depth factor, F gamma D, is by default 1. Okay, so now I can just plug everything over there and find out what would be my Q. So Q basically is gamma D. So this is 0.8 into gamma, which is 17, then NQ, which is 23.18, then 1.54, that my QS and QD is 1.147 plus half into 17 into, that's actually B prime here. Okay, so 17 into B prime, which is 1.3, then N gamma, which is 30.22. Then this one is 0.653 into 1. So this is basically 775 kilonewton per meter square. Okay. Now we have to find out the total capacity. So this is stress, so we have to multiply with the area to find out the total, like load capacity. But when you are trying to multiply with the area, that would be the effective area. Okay, so the effective area, your QU, is basically 775 multiplied, the area is 1.3 into 1.5. Okay, now I have a factor of safety. So Q allowable, that would be QU divided by factor of safety, which is basically 775 into 1.3 into 1.5 divided by 4. That's the factor of safety is given here. So which is basically 378 kilonewton. Okay. So you have to remember two things here again for one-way eccentricity. So what is that? The first thing is like when you try to find out your shape factor, then basically you use the effective length and effective width. When you try to find out the depth factor, then basically you have to use the original length and width. Okay, and the last part of here, this one is actually your B prime, means like your effective width. Okay, now let's move forward and try to see the next problem. So this is the third problem I'm going to solve. You can see this is a shallow foundation which measures 1.2 meter into 1.8 meter and subjected to a eccentric load and a moment. If EB equal to 0.12 meter and EL is equal to 0.3 m meter and the depth of foundation is 1 meter, determine the allowable load the foundation can carry. Use a factor of safety of 3 for the soil. We are told that the unit weight is 17 kilonewton per meter cube. Friction angle phi prime is 35 degree and cohesion C prime is 0. So this kind of problem, first of all, you have to find out what is your EL by L and what is your EB by B, and then see what case you have to follow to find out your effective area. So here you can see EL by L is 0.36 divided by L is 1.8. So this one is 0.2, which is greater than 1/6. So 1/6 is basically 0.1667. So this one is higher than 1/6. On the other hand, EB by B, EB is 0.12 given and B is 1.2. So this one is 0.1. So that's actually less than 1/6. So we can go to see that which case is that. That's actually case number 2 here, which is EL by L greater than 1/6 and EB by B less than 1/6. That's actually case number 2. Okay. For that case number 2, you have to find out L1 and L2. If you see in this figure here, then this is your L1 and this is your L2. So this area here is basically a trapezoid, and that area is L1 plus L2 divided by 2 multiplied by B. That's actually your area of that thing here. But if you want to find out that area, actually you have to find out L1 and L2, right? So we go here, you can see my EL by L is 0.2. So I'm just drawing a line here, and you can see this dotted line here. This side, from the dotted line, this side is for your L2 by L. So you can see for EL by L equal to 0.2 and EB by B is 0.1, then basically you can find out your L2 by L. So here we got our L2 by L equal to 0.22. Similarly, this side is your L1 by L. So EL by L equal to 0.2 and EB by B is equal to 0.1, this line here. So if I take that value here, that's actually 0.865. So we have to find out L1 and L2 from this number here. Okay, now let's go to the board and try to solve the problem. So from that figure, we got L1 by L is 0.865 and L2 by L is equal to 0.22. Okay, now we have to find out L1 and L2 from there. So our L1 is 0.865 into 1.8, that's our L, so which is 1.557. And your L2 would be 0.22 into 1.8. That's basically 0.396. Okay. Now you can see from that figure from where we got that L1 and L2, this is basically a trapezoidal area. So the effective area, A prime, is basically half into L1 plus L2 multiplied by B, which is half into 1.557 plus 0.396 multiplied by the B, which is 1.2. So that's basically 1.172. Okay. Now our L prime is the bigger of L1 and L2. Okay. From the rule of the effective area method. So our L prime is basically 1.557. So our B prime would be A prime divided by L prime. That's actually 1.172 divided by 1.557. So this one is basically 0.753. So once we get our L prime, B prime, and A prime, then we'll try to go back and try to find out our bearing capacity thing. Now you can see for this particular problem, our C is equal to 0. So the cohesion part of the bearing capacity equation would be 0, right? Similarly, we can see there is no water table here and no inclination. So all the inclination factors would be equal to 1, right? So our QU would be QNQ if FQS FQD plus half gamma B prime N gamma F gamma S F gamma D. Okay, so now we have to find out, we know most of the thing, we only don't know like these two here. And we also have to find out our NQ and N gamma for our phi prime is 35. Now we can go to table 6.2, and from there we can find out NQ and N gamma, right? So for phi, you can see your NQ is 33.3, and your N gamma is 48.03. Okay. Now, you have to remember that when we are going to find out the shape factor, then basically we have to use the effective length and width, right? And when we are going to find out the depth factor, then basically we have to use the original length and width. Okay. So let's try to find out the shape factor here. So FQS is basically 1 plus B prime by L prime tan phi prime. That's actually 1 plus B prime is 0.753 divided by 1.557 and tan 35 degree. That's actually 1.339. And then if gamma is, that's actually 1 minus 0.4 B prime by L prime. Point 4.753 divided by 1.557. That's actually 0.806. Okay, now we have to find out the depth factors. So FQD, that's basically 1 plus 2 tan phi prime into 1 minus sine phi square df by b. So you can see DF is 1, and we have to use original width, which is 1.2. So if I plug that value here, 1 plus 2 tan 35 into 1 minus sine 35 square into 1 divided by 1.2, that's basically 1.212. And if gamma d, by default, this is 1. Okay, so now we can just plug all those values here in this equation. So Q equal to actually gamma D. Gamma is 17 into 1. And then 33.3, that NQ. And if QS is 1.339, and if QD is 1.212 plus half into 17 into B prime, which is 0.753, then 48.03, then F gamma S is 0.806, and the last term is 1. Okay, so which is basically 1166 kilonewton per meter square. Okay, so our QU is basically QU multiplied by the effective area. Okay, so this one is basically 1166 multiplied by the effective area. We know the effective area is actually 1.172. Okay, so our Q allowable would be QU divided by factor of safety. So that would be 1166 into 1.172 divided by factor of safety is 3 for this particular problem. So we get 456 kilonewton. So basically this eccentrically loaded foundation will be able to take 456 kilonewton allowable load. Okay. Thank you for watching.